Ready to shoot.
Very good. Hearing no objection, I'd like to introduce Carlos from TAC to talk about DDT. You were exposed to TotalView yesterday. As you look across the Terragrid systems, some of them support TotalView, some of them support DDT, so we want to make sure you have a good exposure to both tools. And appreciate Carlos joining us today to step through that with you. So he's at a slight disadvantage in that he has no local audience, but we appreciate his participation, and hopefully he can give you a good introduction to DDT. So with that, Carlos, I appreciate your joining us, and I'll hand it over to you.
Okay, thank you. So my name is Carlos Rosales, and I work for Texas Advanced Computing Center in the Performance Evaluation and Optimization Group. Today I'm going to give you an introduction to DDT. I'm going to go through several stages, how to configure it to run properly, how to control the flow of information, how to look at data in a fair amount of detail. And then instead of running a lab explicitly today, what I'm going to ask you is that you don't try to run the lab right now, because if we have all the participants trying to run a DDT session through X11 on the login nodes, we could have problems. So what I'm going to do is I'm going to do a guided demo. Feel free to ask me any questions during that time. And you can try this later on at home in your accounts and contact me if you have any problems with that. But let me start with the introduction. Debugging parallel programs is a little bit more complicated than debugging serial codes, because you not only have the usual problems of memory accesses, special cases that you forgot to account for when you were writing the code, or wrong argument to functions, but you also have a whole new set of problems. And these new set of problems are all related to the parallelism that you introduce in your new algorithm. Some of those you can see there in the slides will be things related to the way you have distributed your work. You might have done something wrong in the way that you match boundaries between processors, which is a pretty common problem in MPI jobs. You may have certain racing conditions because you have not been particularly careful when you declare variables as private or shared when you're working with an OpenMP style code. And you can also have problems related to the way that you set up the communication itself if you're working with MPI, so that messages are sent but never really received by anybody, or people in tasks might be waiting for information to arrive when that information has never been sent. So things get a lot more complicated once you get to parallel debuggers. You have seen a lot of this stuff with Led yesterday when he was talking about TotalView, so I don't want to get too deep into that part. I just want to give you a couple of pointers, a couple of reasons why parallel debuggers are really important tools for us. Some people try to instrument their own code with printf, writef statements that would go to standard output, but as most of you will know, these messages are usually buffered by the system, so they will not appear in the order that you expect them in the output. Not only that, but even if you know how to unbuffer things properly so that things appear when they're supposed to appear, you could have way too much information in your hands to process to find out what the problems are. Once you start running at a scale, this is going to be a problem, not only because you have way too much information to process and identify the actual problems, but because these printf, writef, in general I/O statements will introduce delays that could even change the behavior of your code. In other words, using these techniques makes you inefficient, inaccurate, and it takes a very long time to do anything properly. This is why we want a parallel debugger, some tool that can take care of all these things for us. Now, the way parallel debuggers work at the end is like any other parallel application. They're large distributed applications which have an overhead themselves, which is a reason why some debuggers don't work particularly well when you ramp up your execution to a very large number of cores. they're usually divided in this way that you see in the slide, with a front end that collates information from a series of distributed agents, each of which is usually assigned to a particular process or thread. And of all these, only the debugger engine and the front end run on a login node. And you will have access to them through a graphical user interface. The rest are running on the compute nodes with your code. In the case of DDT, these agents are essentially slightly modified GDB debugger instances. So a little bit about DDT. This is the linear distributed debugger tool. It's multi-platform. I'm not going to list the platforms there because it just pretty much covers everything. Supports all MPI distributions, at least that I know of, and is capable of debugging very large-scale MPI, OpenMP, and hybrid codes. Although my own experience is mostly with MPI codes. It has a very comprehensive memory checking and MPI message checking capability, which makes it very useful when you have to debug parallel codes. The graphical user interface, I find it quite useful. It's not full of gimmicks, it's pretty straightforward, and once you start using it, you don't really need a lot of detailed knowledge to be able to run a successful debug session. In terms of scalability, DDT has been run up to, I believe, 130,000 cores, but anything that is above 1,000 cores will show you fairly long delays in the startup, up to a few minutes. However, it's much better at scaling than tools like TotalView. So let me start with the configuration proper and how to set up a debug session with DDT. The first thing that you will need to do is, as with any other debugger, recompile your code with the -G flag and -00. In some cases, the compiler itself will demote optimizations to an 00 level, but that's not always done automatically, so you might want to do that just in case. In the case of Ranger or Lone Star, you would have to load the DDT module. In other systems, what you need to make sure is that the DDT path is accessible from your current path. After that, you will just start a DDT session by calling DDT your executable plus any arguments that your executable requires. Once you do that, you will see a very simple welcome screen where you have essentially three ways of starting the debug session. You can run and debug a program, you can attach the program which is already running, or you can open a core dump file to have a look at what happened in that case. This is for version 2.3. I believe if you go to newer versions of DDT, you will find a couple of new options that include restarting from a checkpoint in a previous debug session, and very soon you will also have available an option to debug essentially GPU codes. But I'm not going to cover that in this introductory talk. So let's start with run and debug a program, which is what most people will do. As soon as you do that, you will be presented with a configuration window that forces you to set up everything right so that you can do a job submission to the backend and run your actual debugging session. You will just see a couple of things: your application name, the arguments that you have typed in the command line if you typed any, and then you will see several sections that you will have to go one by one to complete the configuration. The first section is the options for the type of MPI stack that you're going to be using, and which debugger do you want to use. Which I always leave in automatic, but you might have a reason to change that. There are a few other options under there that I'm not really going to touch because most of them are related to the templates that are usually designed at each site. So the user normally does not have to go into that. Once you set up your MPI version and move on to the next option, you will have to specify some queue submission parameters. In our case at TAC, we use SG as our queue system. In this case, I'm just setting a 10-minute wall time for the development queue. And the one thing that you might want to remember when you try this at home is that project number that appears in the slides, 2010-07-06-HPC, because that will be a code that is already available in our systems and will allow you to actually run your debug session. If you don't specify a project, you will have a failure when trying to initialize the debug session. So keep that in mind, or just grab it from the slides when you need it later on. Once we know the parameters that we need for the queue and the kind of options for the MPI stack, we could just proceed to submit, but my recommendation is to always go to the Advanced Setting tab, which is on the lower left of the screen. That will unfold and will allow you to enable memory debugging, which you can see at the very bottom left on this image. Even a very, very low level of memory debugging, even just none or runtime, will catch a lot of memory problems that you wouldn't see otherwise. So what you want to do is you want to make sure that the box saying preload the memory debug library is ticked and that you have chosen the correct language. In my case, because I don't deal with OpenMP that much, that's usually C, Fortran, no threads. But you will have to, of course, change this to the correct value for your problem. I normally leave heap and advanced unchecked unless I really have a reason to use it. And the reason is that if you make a mistake there, your execution time could be dramatically increased. In fact, you want to be a little bit careful when you select the level of memory debugging, because the higher you set the memory checks, the more it's going to affect your running time. This progression is not linear with the level of memory checking, so don't assume that things are just going to take a little bit more when you increase the level of memory debugging. Just start with a low level and only increase it if you find that you still have problems in the code and you haven't catched them with DDT. And really, unless you have a very strange pathological case, you shouldn't need to go to the highest levels of checking. So once you've checked that, you can submit the job and hopefully wait for not too long until your job is done, starting. You will see a small window that shows you the state of the job in the queue, and it will refresh automatically every few seconds until your session starts. And that's where the fun starts too. You will have this kind of graphical user interface with several sections that are quite important. Starting from the top, you will have some process controls. These are essentially